Welcome to the course on architectural design of ICs. So, till now we have seen different basic building blocks, that means how to design basic building block like this 2 to the power x, then log 2 base x. So, this kind of structure we have seen. So, after that different kinds of adder architecture we have discussed. So, again after that we have discussed there are several types of multiplier, how we can design that, how we can design and how we can implement them for different application. So, that we have seen. Okay. So, whenever we are designing this hardware, at that time the primary thing is that we are basically working in the fixed point number representation. Okay. So, what is there in that means difference between floating point and fixed point? Floating point means actually there I can have, that means the number I can have two part, that means the integer part as well as the fractional part. Okay. But whenever we are talking about hardware, so at that time hardware design, so at that time mainly we are basically focusing on the number which is mainly dependent on the integer part. Unless and until I am, because there is no such that means proper method to represent that decimal point. Where is your decimal point, that you have to notify. So, how you can notify in hardware design? Okay. So, but whenever we are doing that in for implementing any DSP system, so at that time I need to know, or I have to work on in the fixed point domain, not in the floating point domain. So, for that reason, whatever is the algorithm that we have developed, mainly we work on the algorithm on the floating point domain, because we do the algorithmic verification, that is mostly on the that means programming environment using MATLAB or C. So, this kind of language we use, but whenever we are designing one hardware for that particular algorithm, so at that time we never use not never, actually we do not prefer to use C language at that time, because we have to describe the hardware by using any hardware description language, that may be system Verilog, Verilog or VHDL or system C, that kind of structure I need at that time. Okay. So, that means I need to know what will be the effect of doing this, that means changing from the that means changing from means algorithm. In the algorithm we are working on the floating point number representation, but whenever we will come to the hardware, that means hardware design, so at that time we are in the fixed point number representation. So, at that time what is the effect of that, as we are doing this conversation, that means conversion from floating point to the fixed point. So, at that time what will be my effect to that particular circuit, okay, or to that particular algorithm on the hardware implementation side. So, that we will see, that means in today's class, which is this fixed point number representation. Okay. So, what is that, what are associated with that, whenever we are working on this digital hardware design. So, at that time it should be always remember. So, there is an effect for this conversion. Okay. So, what is that effect, how it will affect? So, that we will see in today's class. Okay. So, this is the topic name is fixed point design. So, the first thing is that suppose mostly we use this for DSP algorithms. Okay. So, in DSP algorithms mostly they are being developed in the floating point domain. Okay. So, if you just see this this flow chart, suppose this is my idea about designing any system. Okay. So, in any system means they are mostly that means related to this digital signal processing part. That means there may be several kind of digital signal processing algorithms. Okay. So, now I have to implement that idea, or I have to realize that idea in the real hardware, using the real hardware. Okay. So, whenever we will do that, at the time initially what we have to do, that idea is basically implemented using any algorithms which is basically work on the floating point domain. Okay. So, after that we calculate the range estimation. That means any algorithm that may be iterative, that means in any algorithm we basically perform some of the operations or we implement the function, and then for the function as basically dependent on the operators. So, using the operators we basically do the operations. Okay. So, in any algorithms whenever we are doing, at that time that may be iterative or that may be parallel. So, any kind of algorithm we can implement, mostly as they are working on the floating point side. So, at that time, that means due to this, that means that particular algorithm, what will be the maximum value I will gather or that will be collected for that particular algorithm. So, that initially we have to estimate. Okay. So, what will be the maximum value I can get for that particular algorithm. Okay. So, that we have to calculate. So, after that it is not that infinitely we will run that particular algorithms. Okay. So, there may be certain limitation that how much or what is, that means how much time I will run that particular algorithm or run that particular system. Okay. So, based on that, now we have to do this whenever we will come from floating point to the fixed point, we have to do this quantization. Okay. So, after that whenever we are in the fixed point, that algorithm, suppose we have changed from floating point to the fixed point, then it is ready for the code generation. That means, at that time you can actually, nowadays this EDA tools, they are so much that means advanced, that from that particular, if you just convert it into the fixed point ready data, that means algorithm. So, from that particular point, now you can develop the, or you can auto generate the corresponding HDL for that particular circuit, or that particular algorithm. Okay. So, after that, so the next step, whenever you are having your fixed point algorithm ready, so at that time, that means your algorithm is now ready for code generation in terms of HDL. Okay. And then if you have any targeted system, means as we have seen that we can go for this full custom or semi custom or FPGA based design. So, any of this target system is that only. So, based on that, now you can go for the implementation part. Okay. So, here if you just see, mostly the digital signal processing algorithms, they are being developed in the floating point domain. Later they have been mapped into the fixed point for digital hardware realization. Okay. This fixed point digital hardware, why I need this fixed point digital hardware? Because whenever we are designing one hardware for that means any system or any algorithm. So, at that time my primary target is to achieve these three things, which is that this low area, low power, as well as the maximum frequency of operation, and along with that there this lower that means in production cost per unit, that also I need. That means, these are the things which I have to be remembered whenever we are designing the corresponding hardware for that particular system or algorithms. Okay. So, that is why that in floating point what happens, the corresponding range that is very much wide. Okay. But in fixed point, whenever we are generating the hardware, at that time the range of the data should be within the limit. Otherwise, what will happen? If I just go for the, that means wide range of data, so that means that area requirement or the that to hold the value or to do the operation with that particular length, it requires more number of hardware or more number of logical component to do that particular operation. So, more number of logical components if I need, that means the area as well as the power along with the speed of operation, that means the performance of that system, that will be degraded. Okay. So, that means I have to, from this, due to this floating point to the fixed point conversion, there is an effect which basically degrades the algorithmic performance, but it enhances the, that means this hardware performance. Okay. So, what is that algorithmic performance, what is this hardware performance, that we will see later of this lecture. Okay. So, this float to fixed point conversion required to target, whether, as I said, that the target may be one ASIC or it may be one FPGA based. Okay. So, here whenever we are doing that, all the variables have to be annotated manually. Why I need to be that means annotate that manually? To avoid the overflow or to minimize the that means quantization effects, and to find the optimum word length for implementation. Okay. So, what is the meaning of these three lines? Means, suppose let us consider just one simple example. Okay. Suppose I have to add that means two numbers, that is a plus b. Okay. So, now if I do, that means let us consider 2.35 plus 3.5. So, the result will be 5.85, right. But in hardware, if I just say that this is only fixed point, no, that means fractional point it consider. So, at that time what it will be? It will take only the integer part, which is 2, and the other integer part, which is 3. So, the results will be 5 at that time. But in the algorithm, in actually I need the data to be represented as 5.85. But here, due to this fixed point conversion, I am getting the data as 5. Now, let us consider this particular addition operation I run in a consecutive loop for, let us consider, 100 times. That means, for one iteration I am getting the error for this float to fixed point conversion, I am getting the error of 0.85, right. If I run that same loop for 100 times, that means 85 is the number of error which I will accumulate due to this floating point to fixed point conversion. So, the number 85 is a huge, means what? So, at that time the result will be 585, but I will get, instead of 585, I will get 500. Okay. So, that means if you just calculate the percentage of error, at that time it will be near about 17%. So, that means 17% error I am accumulating because of this floating point to fixed point conversion. Okay. So, that is why, that means now whenever we are implementing the hardware, so at that time I have to do this, I have to find out what will be the optimum word length, so that this quantization error, that will be minimized one. Okay. Just one thing, that is one thing. Another thing is that to avoid the overflow. So, what is the overflow? Let us consider another example. Another example means what I said, whenever we run that algorithms for, let us say, 100 times. So, at that time what I need? I need to represent the data within a, that means within a fixed word length. Okay. So, if I run that particular, suppose that original result is 585, okay, but due to that, this not considering the fractional part, I am getting the result as 500. So, 500 means I can basically represent the data by 512 is the, I think that is 9 bit I require to hold the proper 500. But in actual, if I do something, that means if I that means need more of the data, that means if my to hold the output value, if I take 9 bit, but if my data value or the result value, if it is greater than the maximum value of, that means for 9 bit, what can happen? 511 is the maximum number which I can represent or I can hold. If the data or if the result value is more than 511, so at that time what will happen? I lose the data. So 512, that will be represented as 0 at that time, though the original value of the data is 512. Okay. So that means to reduce this, I have to initially I have to calculate what will be the maximum range of the data, so that I can properly, that means define what will be the maximum word length of the results. Otherwise, what will happen? If I miss any of the bits, so that means that the whole result what I will get, that will be error. Okay. So that is why we have to do this whenever we will convert this floating point to fixed point. So at that time we have to be remember this kind of things. Okay. So this if I say this, all the variables have to be annotated manually for doing this, for avoiding this overflow or to find out the optimum word length. It is basically do it manually, it is basically time consuming, and while doing it manually, at that time you can make the error too. Okay. So that is why you can write the algorithms for that particular to check what will be the maximum that means data range, and then what will be the quantization noise or that means quantization error I am getting, what will be the corresponding that to overflow, to avoid the overflow, what will be the maximum data range, that we can basically calculate using the in an automated way. Okay. So then this fixed point type, that may be two kind of things, that is this word length, another one is integer word length. Okay. So this integer word length means the suppose this fractional portion is basically I have denoted here, and then this portion is basically denoting the fractional part, this portion is the integer part, and this S is the sign part. Okay. So that means the MSB represent the sign, the letter of this represent the integer portion, the magnitude of the integer portion, and this particular point represent the fractional portion magnitude. Okay. So we have already seen what it is the weight of this particular position, that we have already seen. So in the quantization mode, whenever we do this quantization, so at that time there may be two kind of this quantization, that means error that can be due to rounding or due to truncation. Okay. So in overflow, whenever we will that means consider this overflow method, it can have three mode. One of this is saturation mode, another one is saturation 0, another one is wrap around. Okay. So these are the three that means modes of the overflow. So what I said, that manually to do this, calculate this floating point to fixed point, that means to calculate the corresponding quantization noise, then calculate the optimum word length, or to avoid the overflow or calculate the data range. So we need the tools. So that there are several tools which are available in the market. So there is something like this GFix, then Simulink which is from MathWorks, then Signal Processing Workshop which is from Cadence, and then Cocentric which is from Synopsys. So in this particular platform you can check or you can do it in a automated way from floating point to the fixed point conversion. Okay. So why I need this optimum word length? Okay. Why I need this optimum word length? Because this longer word length, what I said, which what we consider for the floating point number representation, it may improve the application performance. That means application performance means as there is no algorithmic error. So, that means the performance at that particular, that means calculation wise, it will be the performance of that particular system, that will be good enough. Okay. But as I am considering more of the word length, it consumes or it increase the hardware cost. Okay. Not only the hardware cost, it increase the that means power too, or it also degrades the speed of operation. Okay. Then again, for that, if I choose shorter word length, it may increase the quantization error and overflows. Means what? If I choose longer word length, so at that time algorithmic error will be minimized, right? That is very much okay. But if I use shorter word length, that may reduce the, or that not may, that will reduce, obviously it will reduce the hardware cost, but it may increase the quantization error. As we in the example we have seen that if we do not, that means for adding this 2.5 with 3.35, so at that time I will get the error of 17% if I run that for 100 times. Okay. So, that means for shorter word length you will accumulate the quantization error more and the overflow will also occur. Okay. So, that is why I need one optimum choice for the word length by which I can minimize the hardware cost as well as I can maximize the application performance or minimize the quantization error. Okay. So, that means all the benefit if I have to get, then I have to find out the optimum word length for that. Okay. So, that means if I just, that means put the curve. So, if I just go in this particular direction, if I put the word length, so increasing with the word length, the performance is basically degraded. Okay. But if I just, that means sorry, if I just increase the word length, that means the corresponding cost is basically inversely proportional. That means the cost will basically reduce. If I just increase the word length, sorry, if I increase the word length, so the cost is also increasing. Okay. But the performance basically, if I just increase the word length, the performance will increase, but this is 1 by performance. So, that is why this is basically decreasing. Okay. So, as this is basically inversely proportional. So, if you just see, then where these two curves is basically meeting, okay, or intersecting to each other, this point is the optimum word length, where the cost is basically, cost along with the performance is the maximum one. Okay. So, this point we have to find out, for getting the, and for at that particular point what is the word length. So, that is the optimum word length for your system design. Okay. So, to finding out the max, that means optimum word length. So, we can have two approaches, one is that analytical approach, another one is simulation based approach. Okay. So, in analytical approach, this we have to develop this quantization error model for feedback system. Instability and limit cycle can occur. It is very difficult to develop analytical quantization error model of adaptive or non-linear system. Okay. But simulation based approach, the word length chosen while observing the error criteria repeated until word length converges and long simulation time. Okay. So, there are two approaches for finding out the optimum word length for that. So, in MATLAB, this basically Fi indicates the fixed point toolbox. Okay. So, if you just write this comment in MATLAB. Okay. So, A equals to Fi of pi, pi means this is this pi function. So, the value will be something like 3.1416015,625. Okay. So, here the data type mode is fixed point binary point scaling, signed is true, word length, that means word length is 16, fractional length is 13. Okay. So, that means among them word fractional length 13 means it represents 13 bit for doing this particular representing this particular terms, and another 3 bit to represent this. Why? Because this is 3 means only 2 bit is sufficient enough, and then I need one sign bit for that, right. So, sign and then another 2 bits. So, this 3 bits is basically left for the integer part, and another 13 bit which is basically representing the decimal part, and then this is the rounding mode. It has chose to nearest, overflow mode is saturate. So, if you just type this on the MATLAB, you will get this information. Okay. So, this FI object that can be you can that means implement, or you can do it for multiplication, keeping the that means keep MSB mode, then addition with keep LSB mode, then for numeric type. So, these are the things which you can do in MATLAB using this fixed point toolbox. Okay. So, for finding out the overflows, okay, there is one this textbook algorithm. Okay. So, that I think in MATLAB that is inbuilt. If you just that means want to know more, you please go through the corresponding reference of this fixed point toolbox in MATLAB. Okay. I think you will get so many help, or as well as the demos are also available on MATLAB. So, you can just follow for that. Okay. So, if you need more on the information about this fixed point toolbox, then you can just that means inform me via discussion forum, that you can do. Okay. So, we will take one example of that, how basically this floating point to fixed point that basically affects the implementation. Okay. So, for that, if I choose one filter implementation as an example, if we choose, so in filter basically what happens, we have the coefficient, okay, and the coefficient values they are basically less than 1. Okay. So, less than 1 means they are basically represented through floating point only, but whenever we will build the filter implementation in using the hardware. So, at that time I have to convert it in fixed point, right. So, for that I need to do the quantization of the coefficient. Quantization of the coefficient means if I just represent the data in floating point. So, at that time the fractional part that may be 32 bit long, okay. But in whenever we will do that fixed point or the hardware design. So, at that time I cannot take that 32 bit long data, because if I take that 32 bit long data, at that time my cost of the corresponding hardware that will be more. So, to get one optimized performance of the hardware, we have to take one decision that okay, this is the optimal word length that which we will consider for implementation, so that the accuracy is not, that means I am not doing any that means the accuracy within the satisfying limit, along with I am increasing the, or I am getting the satisfying performance too. Okay. So, that we will see. Okay. So, and then this in FIR filter, not only the quantization happens with the coefficient, the quantization and the overflow also happens to the arithmetic operation. Okay. So, as in the filter we have to do this multiplication, and then we have to do this addition, where addition is basically happening in a chain. So, that means we have to, in the arithmetic operation also we have to do this quantization and then overflowing. Okay. And for that we have to use this MATLAB tool. Okay. So, for today this is it. In the next day we will see with this example of filter design. In MATLAB basically we have you can or we can do that, okay, considering different that means word length for the filter or the for arithmetic operation, and then what will be the effect on that, or what will be the effect for the transfer function or the corresponding this performance of the overall filter design. So, that we will see in the next class. So, thank you for today.